Hi folks, I'm Patrick and I'm going to tell you about some stuff I've been doing in my teaching lab. So, like all of us who run a teaching lab, we hope that learning happens in that lab. We want a balance of cognitive learning, so knowing how things work, and we want a balance of psychomotor learning, actually doing procedures, the finding out how cooking works school of building a lab. But a lot of older lab courses, traditional courses, or maybe the courses that we went through ourselves as students, were 1,000 easy behaviorist conditioning recipes. You'd get better and better at titrating to that last drop, but with no ability to understand why. I want to say up front, cognitive learning in the lab is not about backing up lecture theory. The lab has plenty to cognate on all by itself, complex lab tasks, building apparatus, knowing when to stop collecting data, choosing a workup additive on the fly, the tasks that separate a bench researcher from someone who's made 1,000 easy recipes. And we want a lab course that builds towards this. But labs don't get that way spontaneously. They actually require quite careful design. So I'm going to loosely and lazily define all of that good cognitive stuff as higher order thinking skills. And a conventional teaching lab has this really sharp increase in that when you hit an authentic research experience for the first time. And this is a problem that maybe some of us are quite familiar with. One of the frameworks out there, not the only one, but one of the frameworks that supports a smooth increase in cognitive task complexity over the course of an undergrad program is inquiry learning, an inquiry lab sequence, and then you've got, for example, guided inquiry right in the middle, has this gradual escalation of cognitive tasks. But there's a gap in first year, and this is my area of expertise. Even in an inquiry framework, the very start often has no inquiry. And this covers the first year in Scotland and maybe year zero foundation or college courses in England, but even perhaps the first few months of an English or Welsh first year will look like this as well. Why? There are a bunch of reasons why we keep inquiry to, say, the second year onward and keep this expository foundation in first year, even when you're doing good things elsewhere. Students have got to practice the basics first. They come from school, they're meant to have done a titration, but how many actually know it? We've got to put them through a basic foundation of reliable practicals, experiments, quote, quote. The resources to upgrade that lab are needed elsewhere. So what are we going to actually do? These are good reasons why efforts to jazz up first year sometimes fall down a little bit. If you want to maybe try and replace that, you find an inquiry sequence off the shelf, particularly guided inquiry work. It tends to be pitched at a slightly too high academic level. Maybe it's a long campaign that you can't make space for. Maybe the context is great a little bit, isn't quite right, and we can't build a new one from scratch because who actually has the time for that? So let's have a look at this reliable but boring foundation, the begrudging expository work that we need to keep in our first year lab for lots of various pragmatic reasons. Let's see if we can spice that up a little bit. So, spicing up existing practicals with features that make them inquiry-like. This is not my idea. There's some really great work in this area already in secondary schools by Saleh and Todt, who modified step-by-step experiments with some inquiry features appropriate to the level of their pupils. These are maybe 14, 15, 16-year-old school pupils. This was a really inspirational paper, came out at the start of my teaching career, and I kind of took this idea and applied it to my first year teaching lab. And I've previously written about this in the Big Yellow Book, and I've called this the elements of inquiry approach. And what this does is it puts these little bits of inquiry, these elements of inquiry practice, nice and early in the lab sequence at an appropriate level. And I've since published another kind of set of these, and that's what I'm going to talk about today. And let's have a look at this rather than talk about what this approach is. I'll just give an example of how I've used it. So one of the things I did there was I took an existing TLC practical, because there's no experimentation in a practical, and I modified it into what I can now, with clear conscience, call an experiment. And I inherited a fairly standard, fairly anodyne TLC practical where students were given a solvent procedure, some reference standards. There was escalation, there was cognitive escalation of a certain type because they started out with a visible dye, and then once they'd practiced the basics, they then stuck it under a UV viewer where things not running are not immediately obvious. But basically, the students ran a couple of plates, calculated a couple of RF values, and learned basically nothing. The modifications that I made to this experiment were all around the kind of structure and the writing and the procedures. And then we start out now with a group exercise introducing TLC. I say write your own procedure because we give the students 95% of a TLC procedure, and we give them a few choices within that. Choices that give the students experience of what happens in a TLC, some cause and effect. And because they're working in a group, they're each only running the same 1 or 2 TLC plates they would do in their solo introduction, but they're dialoguing, they're communicating about various things that influence what makes a TLC good or bad. Choice of solvent. Some of these variables, like spotting below the baseline, correlate to common mistakes in TLC. And this is intentional. I want these students to learn by seeing why something's done the way it is, rather than kind of applying a bunch of theory they don't have yet, but by actually inducing it from experimental evidence. Don't spot below the baseline because it didn't work. And the students then go on to use the procedure that they've written for themselves, which is actually they've converged on a known procedure, but they feel like they've written it themselves. They then take that known procedure and apply that to identify an unknown. The variation they do here is they vary the solvent mixture and iterate to good TLC separations. They'll start with maybe a 10% ethyl acetate and hexane that they make up themselves. Then, the spots aren't very high, iterate to a more polar solvent. Some of them might not really understand the relationship between polarity and spot distance at the start, but most of them kind of get it by the end of the process. Then, once they've got a good separation on their mix of unknowns, they run it against some standards and identify their unknown that way. And this is an example of a plate at the end of the process where students iterated, got that separation nice and good, and then run it against 4 different standards at the end there. But what actually changed in that procedure based on the old expository foundation I inherited? Some of the manual changed. What didn't change? Almost everything else. Same equipment, same solvents, same chemicals, same length of time, same reliability. But what changed for the students? They got this sense of control, they were making meaningful choices that had immediate results, and they learned from their failure. So this is great because TLC is really quick to iterate. I can do this kind of modification without making major other sacrifices elsewhere. What about organic synthesis? You'd think that, well, that's not really that iteratable, it takes much longer. Well, not if you pick the right reaction. We just need it to be fast and we need it to have a good measure of success. Turns out, under certain conditions with the right types of substrates, esters can hydrolyze in 15 minutes at room temperature, and this works very well in screw cap sample vials, so students can do lots of small-scale tests. They also show up really, really nicely by TLC. So how this works is we give the students a partial journal procedure, which again looks like the kind of synthesis you'd write for your own, like a chapter of your own thesis or something. And we give them a couple of parameters to modify within that synthesis. And these are basic parameters. An alcoholic solvent, a cheap alcoholic solvent, whether you put a bit of water in it, a bit of base, how much, what type of base. The students are then given this flowchart about how to actually do iterative experimental testing for the very first time. Run a small-scale reaction, see if it works. Does it work? Great, scale it up. That whole iterative loop is done in a small student group. So again, even though each individual in the group can only do maybe 1 or 2 test reactions, overall you get on the order of roughly 10-ish sets of results. Quite a lot of them don't work because they've picked conditions that don't work. Some of them don't work because just the analysis was a bit off. But out of the entire first half of the lab, the group gets a good set of conditions. Take those, scale them up, isolate it. Single lab session. Just for fun, we then have them do something with the carboxylic acid afterwards, but you can read more about that in the paper. But this approach has some really, really nice benefits. Firstly, failure happens regular, often and small, and it's framed as experimentation. An example, some students ran the ester hydrolysis in the TLC solvents. It didn't work, but they learned that and moved on. If somebody picked the wrong solvent off the shelf in a traditional synthesis lab and burned a day's worth of work, it would either be a safety or an emotional fallout situation. Maybe both, but in here, they just learned a lot, and they learned as a team, reintroducing those social elements to the lab that have been sadly lacking for the last couple of years of social distancing and remote learning. It's also great because I can expand the variable list. Some of those bases, they weren't there in the first year I ran this, but I noticed that people were using them and they kind of worked, so I added them onto the list. If you wanted to implement this kind of elements of inquiry approach in your lab, all you need is a practical with some parameters that could be tweaked slightly and have an impact on success, and some kind of easily understood success indicator, something that you can see test quickly. Lots of different ways to do this. I'd be very happy to talk through the implementation if you wanted to look at an area of your own lab to bring something like this in without having to build a brand new practical from scratch. I'd just like to thank my co-authors who are all final year project students. Lauren and Sam worked with me on the original Overton chapter, and Paul worked on the ester hydrolysis stuff that I've just done. So thank you very much for watching, and I'll see you soon.